Welcome to ECEN 403-404 topic lectures. Today we're going to talk about schematic capture, printed circuit board design, and some debug tips. So this is going to give you some basic background into what to expect when you start designing any circuit boards for this class or anything you might do in the future in your career. So what we're going to talk about is the PCB design process, what is involved in creating a printed circuit board from the conceptual, like I have an idea for something we're going to produce. I know there's going to involve some circuit boards. We're going to have some interconnections, possibly a microcontroller, some sort of peripheral devices, power supplies, such as DC to DC converters and the like, maybe a bunch of analog, whatever it may be. I know I need to get all of this circuitry on a printed circuit board. What do I need to do that? Then we're also going to talk about some of the recommended software to do that because there's a lot of choices out there. And at your stage of development, pretty much anything is going to work. But at the same time, as a student, this is a good time to learn some professional software. You're going to spend a learning curve in developing printed circuit boards, so you might as well at the same time utilize this moment to learn software that could be beneficial in your career. Remember, part of what senior design is about is building you up to be an engineer at some company, out in the workforce someplace. You're going to be working for somebody, you might be designing circuit boards for them, so you want to make sure that whatever you learn is beneficial and could influence your resume. So that's part of what my job here is to help you do, is to make sure you can build up to that point. Then we're going to talk about some of the common mistakes that one tends to make, especially early on in printed circuit board design processing. Just what are those foolish, simple mistakes that we all make and how to avoid them. Kind of learn from some of the best practices, learn from other people's mistakes, what not to do, and try to avoid. Then we're going to talk about some assembly tips. Because obviously we're building a printed circuit board. There's going to be parts that are going to be put on that circuit board. What are some of the tips and tricks that I would recommend for you to when you are hand assembling your circuit board? Eventually, if you're doing this professionally, you're probably going to get this assembled by an assembly company. If you're building large quantities, like greater than say 10,000 units at a time, you're likely to get it made offshore somewhere, and that's fine. And you're going to be getting it done usually by pick and place machines. Wonderful, but you're in senior design. We don't have a pick and place machine. I've had a few students who actually have had access to them, but for the large most part, you don't, which means you're sitting with a soldering iron yourself doing that. What are some tips and tricks on doing that? And then once you have your circuit board, great, you're wonderful. You got your little pretty circuit board with all your parts on it. It's ready to go. It's soldered. Now what? How do I test this board, and how do I go from this to it being integrated into a system, and how do we to do a little bit of system integration testing? So that's what we're going to talk about. So the process of printed circuit board design. Well, first of all, the most major big part of any printed circuit board design, it must start with a schematic. You're going to have a schematic that represents the logical electrical flow of your circuit, and it must be such that it's captured. So this is a process known as schematic capture for the printed circuit board. So similar to what you have done in the past with simulating tools like Multisim and or PSpice, you're going to have to create a netlist, because the printed circuit board is really a netlist that has what we call footprints, or the physical mechanical outline of the pads, the solder pads for a part. So there's the symbol, as is known, the schematic symbol, where, like for instance an op amp, the triangle with plus and minus, and then there's power and ground, or VDD and VSS could be plus or minus 15 volts. You can have null pins, and then you have an output pin, say pin 6 on like an LM741 op amp or an LM358. So you got pins 1, 2, 3, 4, 5, 6, 7, 8. Each pin has a representative purpose. So I have a symbol that represents that part, and then there's a footprint. It could be what they call a DIP inline, dual inline package, a DIP package 8 pin, in which there are 8 little holes with a certain little solder pad, and you push the part through the board and then you solder it to it. So there is the symbol and there is the footprint. So the first thing you have to do is create a schematic that interconnects all the symbols. The op amp symbol gets connected to the resistor symbol, gets connected to a connector. That's one of the very important things. We're going to be talking about that. And then from that schematic capture, you're going to produce a net list. Again, just like you have with a multi-sim or PSpice, you have a net list that represents all the interconnectivities for each particular node of your circuit. And then once you have that, you're going to produce and place and route a printed circuit board. You're going to define a shape of the circuit board. You're going to import all the net list and all the parts. And then you actually have to place the components in some logical arrangement such that it's relatively straightforward to route. And then you actually have to route those lines. And then you need to verify that the printed circuit boards meet all of the manufacturing rules. Because in the end, the circuit board has to be produced. And you can't just say that, we're going to use 1,000ths, 0.0025 millimeter traces, and the printed circuit board manufacturer who's actually got to physically produce your board on a material such as FR4, which is a fiberglass resin material that has copper clad on both sides, has a gap of about 62 thousandths of an inch, 1 ounce of copper foil, and they have to photo etch. What they do is they take and put a photo plot of your design on one side, another photo plot on the other, expose it with light. They actually develop your board, just like they would in the old days of developing photographs. They actually develop the circuit board, the photo resist, as it's called, the resist an acid bath, and then they spray your board with some sort of hydrochloric or similar acid, which then causes the copper to melt away and dissolve, and the only thing that's left is the resist exposed copper. So that copper has not dissolved away, and then they clean the resist off, polish the board, scrub it really good. And then usually at that point, you either do solder mask over bare copper, which is just paint, silk screening, just like you would silk screen a T-shirt. So there's all of these mechanical processes that go into producing a circuit board. Well, there are certain rules that you must follow for that circuit board to be manufacturable, and for them to say, the files you provided me, we guarantee that the files you gave us is the circuit board you have in your hand. So for that to occur, you have to have a set of rules that they get met. In that process, you will then produce what's known as a CAM file. So we start as CAD, computer assisted design here, but in the end, you're going to produce what is known as CAM, computer assisted manufacturing. You're going to produce files that the circuit board shop must use for manufacturing. So you're going to go all the way from schematic all the way to CAM files. That is your responsibility. So schematic capture. So again, what I always do personally is I always start with a block diagram of the system. I know I've mentioned this also with the microcontroller lecture, and I've mentioned this in any part of the lectures that I give on how to define your project. You always start with a big picture. Why are you building what you're building? What is it going on? Big picture. At some point in the block diagram of your project, there's going to be your circuit board. There's something that you're doing. It's a DC to DC converter. Maybe there's some audio inputs, maybe some video. There's an LCD screen, for instance. There's a touch panel. There's a couple pressure sensors, temperature sensor. We're controlling a motor or a stepper motor, something along them lines. I don't know. In the end, you have a block diagram that describes your system. So you need that. And like I said, eventually you have a block diagram that describes your board. What is its inputs? What is its outputs? What kind of, if there's a microcontroller, what is it? What is it connected to? Every project that I work on, I have a block diagram. Personally, I like to use Visio. It doesn't matter what you like to use, Smart Draw, Paint, doesn't matter. Just come up with a diagram. It could be on a whiteboard. You just need something to help you organize your thoughts, because having that first allows you to then select all the parts. And I mean, and this is what I personally do. I select every single part down to the manufacturing part number. In other words, go to DigiKey or Mauser or Arrow or Avnet, whoever your favorite vendor is that you're primarily going to be ordering parts for. Probably in this class, DigiKey and Mauser. So that includes all resistors, capacitors, ICs. So pick everything. Start with the block diagram, kind of draw out your schematic. More than likely, you probably have simulated your circuit in some forms. Like let's pretend we're designing an operational amplifier type circuit. As such, you probably have already simulated your circuit, which is great. At that point, you pretty much know all of the component values, you know the ICs, etc. Now you really do need to pick what is the package, because you just can't say LM741 because there are a variety of LM741s, which, by the way, I'm not the biggest fan of the LM741. There's a whole line of better op amps. We teach the LM741 a lot in our op amps classes, stuff like 325, etc., because they're easy and they're cheap and they've been around forever. But if you're going to put that into a project, I'd probably would choose a different op amp. There's a host of better op amps. Just a side note. Anyway, so you pick your IC, and if you just choose, like for example, LM741, and you've got to choose the package because there is a dip package, there's what's called the SO8 surface mount package. You can buy little op amps that are the size of probably the size of a grain of sand. I mean, you can buy really tiny little op amps or the size of a grain of rice, real small op amps. Same thing with resistors and capacitors. So you need to choose the package that matches the symbol that you're going to use. And then you're going to create a symbol for that part, like I've mentioned with the op amp, basically the little triangle symbol that we're used to seeing. So you're going to have to create that symbol. Um, every editor, every PCB editor has a way of doing that. Eagle has a way, Altium has a way, Pads, Allegro, you name it, every editor has a way of first creating a schematic symbol library. It's called usually a symbol library. And it just literally is a pin, like pin 1, pin 2, pin 3, connected to some visual drawing of the part. And again, a resistor, the resistor symbol, a diode symbol, etc., etc., etc. Pretty straightforward. Then you're going to actually design a schematic. So you've already gone through this probably with your multi-sim simulations you've done in the past. You've got a symbol for an op amp, resistors, capacitors. You drop that into the schematic page, you connect everything together, that creates your design. Now, if you have a complicated board design, then you're going to use something called a hierarchical board design. And I'm going to provide an example project in Altium, because I'm a big fan of Altium. So if you ever work with me on printed circuit boards, you'll probably hear me talk about Altium. I've been using Altium, it kind of dates me, since it was known as a product called Protel, which actually dates back into the early 1990s. So it's been around a little while. I've been using Altium since then as my predominant software for printed circuit board development. I've been doing PCB development for about 25 years, and in 25 years, that's pretty much all I have ever used. I am familiar with other ones. I've also used OrCAD, I've used Allegro, I've used Pads, and I have used Eagle. I, in fact, keep a copy of Eagle. I don't like Eagle, but I keep a copy because my clients like to use Eagle sometimes, and most students like to use Eagle because it's free. There's also KiCad and a few others, and we'll talk about this a little bit when we get to the software. So, the point of this is that there is a thing known as hierarchical board design, where you actually design tiers. You basically start with a block diagram and you work your way down into sub-circuits that are connected through the block diagram. So here's just an example of one of the block diagrams. I have a project. Again, I like to say this is straight out of Visio, it's a screen capture. I have a voltage reference. I'm going to basically a potentiometer is what this is called, a thin pot. It's basically a potentiometer. I'm using a PIC processor, and this one's a PIC 18F2458 that has a built inside A to D converter. So this is going back to the microcontroller lecture where you have built-in peripherals. I have a little box that just says firmware, so that just tells me, even though it's obvious that, I have a microcontroller. It just means there's going to have to be firmware written for this processor. I have two switches, a max scale and a zero. These are just push button switches, showing that I'm connecting that also to the microcontroller directly. I'm taking 12 to 30 volts as my external voltage off board. I'm going to come in through some connector, and I'm going to have a DC to DC converter on board to provide power to this entire circuit. So I usually just label it this. I'm kind of aware of what voltages I'm going to need, usually 3.3 volts. I have a bus called the SPI bus that connects these two chips. I have an A to D external A to D converter because or digital analog converter, excuse me, an AD421. This is a current loop DAC. And then I have a completely separate DAC here that was going to be for 0 to 10 volts to produce. So this would do 4 to 20 milliamps and 0 to 10 volts. Basically, it was just a translator that go from a mechanical input of a potentiometer to either a voltage output and or a 4 to 20 milliamp DAC. So a real simple circuit here. I actually have produced this circuit. This is actually in production now. So once you have that uh, diagram, you now have to select parts. So it means you're going to go to DigiKey, and I like DigiKey, especially like their website for selecting part. You literally type in the word capacitors and you get a list. Same thing with microcontrollers, and you have this down selection of all of these different, component pieces of the parts, the manufacturer, the packaging, the series, things like that. You got to choose what's most important to you. Usually, like when it comes to capacitors, that it's ceramic or it's electrolytic, and that usually has to do a lot with the equivalent series resistance. You have to pay attention to things like what capacitance are we going for? Are we going for 1 microfarad or are we going for 1,000 microfarads? Makes a difference. If you're going for a microfarad, you're probably going to use ceramic. If you're going to go 1,000 mics, you're going to probably be using electrolytics. If you use electrolytic, you got to pay attention to polarization. You probably remember that from some of the previous lectures you've had in 325 and 214. So you're going to get a list of different parts. And if you notice here, the first part, so I typed in here, I wanted a capacitor. Notice that it chose initially 0201. And you probably remember from microcontroller lecture, I say avoid this part. Well, this is why I highlight this and I keep mentioning this over and over again. Make sure you avoid the 0201s or similar parts because they come up first for whatever reason in a DigiKey search. Which means if you're in a hurry and you're trying to pick parts for your board, you can type, I need a 0.1 microfarad capacitor. I don't care, it's 2 volts. I don't care what the voltage is. It's always going to be greater. That usually, like the default voltage on these are usually like this one here is 25 volts. So if you're doing a 3-volt circuit, you're fine. So this part might be perfect for you in all electrical considerations. Mechanically, though, it's an 0201 package, which means it is extremely small. What that literally means it's 20 thousandths by 10 thousandths. Extremely small. We're talking size of hair small. The tip of your pencil, your mechanical pencil tip, is larger than this component. That is how small this is. And it is the first part that is selected out of DigiKey. So if you're in a hurry and you go ahead and jot down this part number, into the vendor or the manufacturer part number, guess what you get? You get this part. You're not going to be able to solder it. Normally we have at our blitz, which for the fall of the semester we don't really get because of the COVID stuff. But normally you have blitz, and usually during that I offer soldering services. I will not solder these parts. These are one of the few parts that I throw my hands up and say I'm not doing. I have successfully soldered 0201 personally once. It took me about 10 parts to do it. I thought it was luck that it eventually just stuck to the board and I was able to kind of rough it in there. I swore I will never use an 0201 personally by hand again. I do use 0201s in designs. They are machine assembled. So again, another thing I'll also mention towards the end is avoiding BGA, but you can see here selecting parts like for the chips, so you have little tiny microcontrollers. Um, Notice this little part, this little 6-pin microcontroller. It's a really small, like SOT236. You can solder this. I mean, this is about the size of basically a rice grain. So a piece of rice is an actual microcontroller. Believe that or not. I was mentioning that in the microcontroller lecture. If all you're trying to do is maybe read a voltage and just turn on and off a sensor or a solenoid, here you go. This little cheap microcontroller. Um, so it's what 38 cents for this in quantities of 3. So you can imagine in high quantities these are extremely cheap. So next thing you know in schematic capture, you need to examine the data sheet. So, you get pick a part, great, but you really do need to pay attention to the data sheet of the part. It tells you everything you know. So like here, I pulled up this PIC 10 that we were just looking at, a little 6-pin 8-bit microcontroller. Um, this is fantastic. You got to pay attention to things like the temperature. You need to determine the part type, review the specifications, etc. Make sure this part meets your needs. Don't just pick a part because that's what you've been using or what I used in 325 or what I used in 248. Boy, we used this FPGA, blah, blah, blah. Pick the part to meet your specification. That's why we've gone through all of this effort about you writing CONOPS and writing requirements documents. There was a reason for that. So that when you pick parts, you pick the part that matches the project. You allow the project or product, whatever you're doing, and then as a project, define what it needs instead of you defining what part and then trying to fit the project to it. So very important. So make sure you review that. Then you're going to select the symbol. And I'm going to show you that here. So you got this part, and then that ends up making a symbol. Now you can draw your symbol like this. You can organize that. The thing is, this is a symbol. You do not have to put things in pin order. Now notice that they put pins 1, 2, 3, 4, 5, and 6 in order as it physically as it is on the part. I don't like to do that with my symbols for microcontrollers. One, I mean, unless it just so happens that it's organized well, I like to group everything by ports and functions. Remember, this is just a symbol. This is not the actual physical representation of the chip. Now, I notice a lot of students, and quite frankly, a lot even professionals, once you're out in a career, they'll design a schematic and they just stick with the layout of the chip. That's perfectly fine if you do that. It's just what I have found, it makes it hard to follow your schematics because you end up with lines all over the place, which electrically still correct. But remember, the schematic, the way I do it and philosophy that I follow in a schematic is I want my schematic to be easy to read such that when I'm debugging it and or fixing it in the future or trying to explain it to another engineer or whatever the case may be, I'm trying to show this to the client, that it's easy to follow and that it looks good. I mean, I'm probably an odd duck in that. I like my end products, which include documentation, to look good. I don't want it to look like a rat's nest. So I actually take a lot of pride in my work and make sure I take time and draw things out professionally. So the symbol again can be modified to fit your schematic style. And then after that, you actually have to create the PCB footprint for the part. So you got a symbol, but then there's a footprint. The footprint is also in the data sheet. Now, 9 times out of 10, some data sheets reference another data sheet, or an application note to say, this is the blah, 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 like a DIP 8 footprint. Everyone knows what DIP 8 is. If you need a DIP 8 footprint, you go here. I mean, there's some data sheets that are like that to save an extra page in the PDF nowadays. They reference another document for the footprints. Just mention it. It is this footprint. It is, in this case, an SOT 23 6-pin footprint. Go see page whatever on this other document. But in this particular data sheet here, they actually give you the footprint. And a lot of them also give you not only the physical mechanics of the part, but they actually give you the recommended what they call LANDS, LANDS, PCB footprint design. In other words, exactly the pad dimensions, the spacing of the pads, how that should be done, so that you can actually properly create that symbol to or matching the footprint to the symbol. Pad 1 is this dimension, pad 2 is this dimension. So creating symbols. So here's a much larger microcontroller. So this isn't the little 6-pin that we were looking at. This is actual symbol here. This here is looks like a 20-pin microcontroller. This is a PIC 16F690. So I have quite a few microcontrollers in my microcontroller library. So this is a file that I have. That's my microcontroller library, and I have all of these different parts. I labeled this one PIC 16F690. And notice I grouped all the port C's here. I grouped all the port B's, power and ground, so VDD and VSS. I put on one end. I put port A functions here in order, 0, 1, and 3. There was no 2. Well, no, excuse me, 2. This here was the clock functions. So everything that had a separate function, I kind of grouped up separately. So the idea was that I would have a very organized schematic depending on the functions I was performing. In other words, I could have laid it out, pin 1 here, pin 2, pin 3, or put pin 1 here, 2, 3, 4, but it would have gone pin 1, pin A5, see pin 3 was, where's pin 3? A4, pin 4 was this one, so on. It didn't quite flow. This right here, for instance, is the programming connector. So this is how you program the parts. So I kept this separate. This is the oscillator. I kept this separate. And then I use these pins for actually doing base functions. So like I said, so this is the symbol, and it just is a pin, and this is just simply a rectangle, a blue drawing. It's just a rectangle. The blue outline here serves no electrical purpose. It is just there for me to have a draft. The only electrical component is the pin, and it has a pin name and then the pin number. And of course, usually built in is wherever you want the designator, like U1, U2, 3, or R1, R2, R3, or C1, C2, C3, where that goes, so on and so forth. Once you've done that, you create the footprint. So this is a different footprint for a different microcontroller. This one here looks like I have to examine here, but this looks like this is a 48-pin TQFP package. And so we have the pins all laid out. This starts at pin 1 as a rectangular pad and loops itself around in a counterclockwise fashion. And these pad dimensions are provided in the footprint. You know, that's its width and length, if you will. The size, the X and Y dimension is provided. And these are the same pads, just rotated 90 degrees, so on and so forth. Each one is independently numbered. There are some wizards and almost all the tools for doing this. I still kind of old school. I actually do these each one by hand or copy and paste them, but I personally set them and verify all the dimensions. And with Altium, you can actually drop in 3D, what they call step files, 3D components mechanically on top of this. So you can actually download from the manufacturer the 3D drawing of your part integrated into Altium. So you can actually verify visually, mechanically it matches your footprint because you can actually see the part. That's really useful. It saves a lot of trouble because I can't tell you a number of times, especially in the early days when that was not even a feature, didn't even exist. And if you made a mistake in the footprint, you got the circuit board back, you spend a couple $1,000s in circuit boards, and the footprint's wrong, it's a bad day. So always double check your footprints. So the schematic capture process. So now we've had all our symbols. I now actually created a schematic. Here I'm using this comparator, this op amp here. This is an AD8629, and it just has the actual manufacturer part number, full up part number. I actually put this in Mauser DigiKey. That is the part number I would use to order. My bill of materials has the part numbers already built in. The parts I have, there's other fields that are hidden for display. It includes the part numbers of my resistors and capacitors, but I include that because when I build my bill of materials through Altium, it populates an Excel spreadsheet with all of those parts. It's pretty cool. So I know every part number here on the board as I'm laying out the schematic. So I drop these components in the schematic editor. I got everything labeled. I got my ports. So this is part of the hierarchical design. I got ports coming in. I've got, these are transient voltage suppressors for voltage spikes like lightning and stuff. Clamps, diode clamps. like I said, amplifiers, feedback circuits, or reset circuits, all sorts of things like this. This is for doing what they call turbine flow measurements. So this is getting a measurement that's coming across the field, probably several hundred feet away, exposed. So there's a lot of noises coming in, and we're trying to measure pulses, basically pulses per barrel of oil flowing, and to provide a simple digital output that a microcontroller could read. So we have a real signal coming in from the field through a connector, and the output is a digital interface to a microcontroller. So I've captured this schematic. I drew this point by point, labeled my power. Notice I use multicolor for power. You don't have to do anything like this, but this is what I do to label color and ground. Everything is specified. It's this again, this is why I do this. It's very easy to see the flow of the schematic through the circuit. Here's another example. This is a one-page schematic for a little circuit for a company up in Dallas. And this here is a little DB9 connector. It has an adjustment pot. There's a little regulator here. It takes power in and produces 3 volts. This is a real simple little simple switcher. Highly recommend this, by the way. I have got tens of thousands of these DC to DC converters have been using over the years. Probably close to 100,000 of these been produced. Of course, millions of these are actually in the field with, probably now tens of millions. This part's produced probably even more than that. Honestly, this thing's been around since the late 1990s. This replaces your voltage regulators, your LM7805s and stuff that you would have learned in earlier classes. This here will take anywhere between 8 to 30 volts. Really depends. Really, it made for 8 to 42 volts, I think, on this. It's all really limited up for me to these capacitors right here. So this is designed to take 8 to 30 volts in and produce, in this case, 3.3 volts out. But it's a DC to DC converter. It's called a buck converter. So the efficiency of this converter is about 90 some odd percent, like 93%, which means the amount of heat produced is negligible on this circuit. If I would have put a 7805 or 78, basically an adjustable regulator down to 3.3 volts, this thing would be roasting hot if I put in 24 volts, which is actually the feed-in voltage on here. So if I put in 24 volts, I'd have a heater on my hands. So very important. You'll hear me talk about DC to DC converters in this class a lot. And if you're presenting me a circuit in the presentation updates and you're doing like, here's my power supply and I used a 7805, I will bark back at you to not do that. So here's an example of a simple DC to DC converter that you can do. And here's a little 8-pin microcontroller. So this is a perfect example of a perfectly sized circuit using an 8-bit micro. This one's a Texas Instruments TI MSP430. You can also use a PIC. There's a variety of different 8-pin micros out there, and like we were just looking at a 6-pin version, taking in an analog digital signal and taking another set point. So basically 2 different set point, 2 different analogs coming in. So that's using 2 separate A to D inputs, and then doing some algorithm inside, and then controlling an air solenoid here on the back end. This actually controls a solenoid, and using a transistor to control that. So this is a one-page schematic. A hierarchical design looks like this. So this here is a design I did a few years back. Notice the sheer amount of pages. A moment ago we had 1 page, and here we have a lot of pages. This one was probably about a 3-month design. Probably by the time I started the design to the moment the boards were in hand and being tested was probably about 5 to 6 months in the end. And this is the first page, the main schematic up here. Notice how it kind of flows. It has root schematics, and then they break off again. So there's another page here that looks similar to this on this a single board computer page, SBC, that breaks out. So, but you notice the main schematic is real simple. There's a power system, there's a main connector, ESS connector, an FPGA. The FPGA connects to a single board computer, and then there's another connector. So there's 2 main connectors. These are for the VME bus, which is a VESA mezzanine connector bus. So a very proprietary type bus technology. And then this is a power system for the entire system. provided all the power to all of the different components. So that one just provided rail voltages like 3.3 volts, 5 volts, 12 volts, so on and so forth, 1.5 volts, 1 volt at high currents. All of this was done here and just provided for the support for the rest of the circuit. So really, this right here and this connector, this right here was there because I needed the connector because to fit into the chassis. But you notice I didn't even use the connector. So all of it's they got these little red no DRC, basically do not check because it's not connected to anything. So really, this entire complicated schematic, which when printed out on 11 by 17 paper, it's like a half-inch thick. Um, it's just in the end 3 main blocks. So it made this a lot easier to when you're debugging something. If I only had to deal with the power, I just paid attention to this block. So now you need to create a netlist. So I know this is kind of a long lecture, and I apologize for this, but I'm trying to give you a lot of detail on printed circuit boards here because this is something that you are going to be dealing with. So you're going to be creating a netlist. So at this point, usually this is an automatic step, and it's really based upon the software that you're using. So if you're using Altium, it actually compiles the schematic. You actually literally will, if you do import into a printed circuit board, it actually will go through a compilation step. It goes through, builds a netlist, verifies a bunch of rule checks on the netlist to make sure inputs are not connected to outputs if you've got pins defined as such. It looks for those basic silly things that you left a pin not connected, that kind of stuff. That's where I had to have those little red DRCs so that the little X's so that you actually tell the compiler, hey, I'm truly meaning to do this and it's okay. You don't have to warn me. So you do this, and you go ahead and you compile that and you import that into your PCB editor. Now you're going to route your schematic, and you're going to have to set all these design rules. For instance, you look here, my design rules for this printed circuit board is set to 5/1000ths of an inch. Most, especially American-based PCB shops, are still typically done in thousandths of an inch, what they call mils, M-I-L-S. That is pretty common. Um, Other regions of the world also still use mils, but also millimeters. So you're either going to be working on mils or millimeters. And in Altium, you just click the letter Q and it switches between the units instantly. So it's a really useful feature to go back and forth. Quite honestly, I use both pretty much, half one, half the other. I go back and forth in the same project between millimeters and mils all the time because some data sheets, especially a lot of mechanical parts, are all still listed in thousandths of an inch, whereas a lot of your parts from like, your circuit board, typical components like microcontrollers, capacitors, etc., most of the predominant units is metric millimeters, which would make sense. I tend to lean more towards millimeters in designs, but mils is heavily used. So I've just kind of got used to doing both and being able to translate in my head. Again, always pay attention to the units. Always make sure you look at the units of measure because you don't want to make a silly mistake where you do something in thousandths of an inch and it really should have been in millimeters. So always verify that. So you set all these clearance rules. What is the clearance? Most circuit board shops do 5/1000ths of an inch trace and clearance, meaning that you have to have a clearance between any other copper to the edge of your copper is 5/1000ths of an inch. I will point this out because this will happen because it has happened. Do not get into an argument with your printed circuit board shop because they will win. They're the ones building your board. If you set your rules to 5/1000ths of an inch and they come back and say that one trace is interfering with another trace and it's not perfect 5/1000ths, and you come back and say, well, I told Altium it's 5/1000ths of an inch and it says it's okay, they're right. That means that if they're showing you something, you might need to nudge a trace. Altium is going to do the best it can to flag if this is less than 5, in this case 5/1000ths. If you set it to 10, it'll be 10. But sometimes the way it computes the geometry is a little bit off, and versus maybe the CAM software that they're using on their end. Because they might be using some older software, because they might have been in business for the last 40 years and they're still using some old software, and the way it computes the geometry is different than what Altium's doing in the latest revision. It doesn't matter. You're arguing to a brick wall. They deal with circuit boards at a volume level. Their job is to get your job on the floor to get processed. If they're telling you to move a trace, move a trace. Don't go back and forth. The reason I'm highlighting this and spending a moment talking about this is that this happened a couple semesters ago, where I had a student, I kid you not, spend 2 weeks going back and forth with their printed circuit board manufacturer, one of the ones we heavily use in this class, and they were arguing literally about a 5 thousandths clearance gap. And he kept saying, "Look, I've got the clearance. It's 5 thousandths of an inch." And the CAM editor, customer service representative at, I think it was at Advanced Circuits, was like, "No, we're computing 4.9 something something thousandths of an inch. We're not going to build this because we guarantee our boards." And my student kept going back, and he would ask me about it in lab, and I was like, "Well, just move the trace." But he's like, but it says 5 thousandths of an inch. I'm like, "I don't care. You're going to have to move the trace." Well, he kept futzing with it, and eventually it cost him in the end about 2 weeks. It took to the second lab to finally convince him, like, "Look, you're not going to win the argument with them. You know, that they've got 10 other boards right after yours that are going to do. You're just one little email and one little board order. Trust me, your $30 board order is, not a major concern to them. So if it doesn't meet the rules, then they're just not going to build it. So make sure you meet all the rules. All the rules are posted on their website on what it is. And if you use the EDC's board fabrication facility, they have the same rules. In fact, theirs are usually what I call more stringent because they're going to use the different type of technology. You will spend a lot of time doing placement. Define the board shape and the mounting holes. This is driven usually by your mechanical designs. The beautiful part about being in senior design right now is usually the mechanical definitions are yours to define. Usually you're not having to try to fit into some incredibly small enclosure. You're not having to deal with some weird shape. As a embedded systems and electronics developer and consultant, I'm usually the last person the mechanical engineers consult. I'm usually the one that they call at the last minute saying, "Okay, this is the space we have left for you." And usually I look in the volume that's left. I'm like, "I'm supposed to put all of this?" You know, you do realize the client, the final client here, the project actually has us, using like 4 processors and, 8 connectors and, all these weird powers. I've got to dissipate 30 watts of power, and I've got to do this to I've got this list of mechanical requirements that are tremendous. And they're like, "Yeah, yeah, but this is what space we have left." I usually have to beg, borrow, and steal additional space somewhere. Well, the good thing is in senior design, it's typically not a problem. It sometimes is, but usually it isn't. You can buy your own enclosure, make your own enclosure. So this is the one time that you can actually define the board shape and allow your parts and your layout to define the board shape. So eventually you're going to import your netlist into PCB Design, and then you're going to place the components. Some parts have a special position. Obviously things like connectors. You don't want to put a right angle edge connector that's going to be plugged off board, like it's going to be exposed to the outside of a box in the middle of the board. Again, say this because I've witnessed it. So make sure you place the connectors in the appropriate space. Some parts need airflow. Some parts are going to get hot. If you use, like, for instance, a voltage regulator, which I would highly not recommend unless it's a special analog function, and we can talk about that personally, you're probably going to need airflow because it's a hot part. It's going to get hot, which means if you put it in an enclosed box with no airflow, it is going to get even hotter. Because if you think about it, it is generating watts, joules per second. As time goes by, that integrates, and so the space starts to heat up. So you need airflow to reject that heat. So always pay attention to that. examine your design and group all parts together. If you have a connector that goes straight into the microcontroller, it would make sense that that connector has a straight shot to that microcontroller, especially if it's a multi-pin. Like I commonly do this. I put an extra I/O connector on a board if I've got the space, just because, as I mentioned in the microcontroller lecture, you never know. I might need some extra I/O lines for development, especially before the thing goes into production. And then that part becomes what we call do not populate, because copper's free. Remember, they are etching away copper, so I'm paying for that sheet of copper, so it doesn't matter what I do with it. So if I have a connector I've got to route to a microcontroller, I'm going to put the connector right next to the microcontroller and make it easy. So make sure you group everything together. Look at your rat's nest, your net list, once it's exposed, because you usually get to see when you import the design, you'll see this rat's nest. And place parts that you do not have, just take a look and kind of balance out the rat's nest so it's not all grouped up in one area. And above all, do not use the auto router. I repeat, do not use the auto router. There is very few times that I've seen the auto router really do a great job. And I can guarantee you, in senior design, I have never seen an auto router do a good design. If you want to see an example of why I hate auto routers, I have my senior design project that I did 25 years ago. That looks like crap. It forgot the power and ground pin for every single part. So I'll admit I'm a little biased. But I have used auto routers since then, and I have actually seen auto routers do a halfway decent job. In fact, I would say I have one of my friends who's a PCB designer can use an auto router and do a fantastic job. Um, the only problem with that is he spends just about as much time setting up all of the rules to do the design as I do in hand routing a board. So it's kind of mocks nicks. In other words, it kind of cancels it out. The time saved in routing, physically routing the board, is kind of counteracted with all of the different rules for all the different types of nets. Power and ground need to be routed like this. I want to use this type of via. If it's these signals, do this. If it's these other signals, do this other thing. There's all sorts of ways you can do that. If you set it up and appropriately set up regions of your board, you can route it really well with an auto router. Only problem is that most people who use an auto router do not do that, because the whole point of an auto router in their mind is to save time. So they're already kind of predisposed of, I'm not going to set any rules, I just want the auto router to go. Well, if you don't constrain it, you get a mess. And that's usually 9 times out of 10. I've used auto router here not too long ago on a test circuit board. It's not something for production. It made a mess, but it worked because all I needed it to do was connect A to B, and okay, it was ugly, but I didn't care. So if you don't care, then use an auto router. If you care and you want your board to work, use an auto router. Another thing that's good also about hand routing your board is you actually have putting eyes on the trace in question. If in your head you're looking at your schematic and you're going, pin 1 is connected to resistor 1 connected to connector 5, pin 3. Well, if you're watching your schematic, and I usually use 2 monitors while I do this, I have a printed circuit board on one screen and my schematic on the other. I'm actually watching my schematic on one screen, and I can actually go, yep, that matches my plan. And then I can also look at, usually have the block diagram as a printed out beside me, and I'm verifying my design as I'm laying out the circuit board. So that's why I usually have a high chance of success that when I get my boards back after spending a couple $1,000s on the design, stand a fair chance that it's going to work, because there's so many steps and checks along the way. And one of those steps and checks is hand routing the board. Trace size matters. Use a trace width calculator here, because trace widths are set by the current being used on the track. Do not expect to be able to drop 10 amps on a trace on a 10 thousandths wide little trace. I mean, if you need 10 amps, that's fine, but you're going to have to make sure that it works, because if I throw 10 amps, and this is from this trace width calculator, this is from Advanced Circuits, they provide this free to you to use. Do not change this optional inputs here for temperature rise. This is pretty much a good setting for ambient temperature and trace length. The only thing that changed is the length. That's the only thing that matters here. So if I'm punching 10 amps through a circuit, doesn't matter the voltage. If I'm pushing 10 amps, because remember it's I squared R, 2-ounce coppers. This is actually probably even thicker than normal. So this is the defaults. If you get a number out of here that you don't like, then it's definitely not going to work for the board you're going to get produced in this class, because it's going to be even half, because it's usually 1-ounce copper. So 10 amps at 2-ounce copper with a 10-degree temperature rise with 1 inch of copper, one little inch, requires an external layer. That means your top and bottom side of a board, not the inner layers. Because with a circuit board, you can have multiple layers. That requires 142 thousandths of an inch, so greater than 1/8 of an inch. So keep that in mind when you're laying out a circuit board. If you're dealing something like 1 amp, you can get a pretty low resistance. So when you show me your PCB designs, I'm going to ask you, what is the current that you use? So pay attention to that. The layout process will take time. You need to be patient. This is a slow process, and physics matters. Don't think just because you're in senior design, somehow physics flew out the window. So if you're doing high-speed signals of some kind, you're doing gigahertz or high megahertz, like 500 megahertz designs, voltages, currents, impedances do enter circuit board design. Just because you took 322 and studied microstrips, and now that you're in senior design, and you've made an A in say 322, doesn't mean microstrips don't still exist. Guess what? Microstrips still exist. If you're dealing with 500 megahertz signals, physics matters. You're going to have to think about impedances. And there are tools for this. This is called Saturn PCB Toolkit. You can download this for free. I keep this on my computer all the time, use this all the time. I actually work with my PCB manufacturer. Actually, in this case, I use Saturn and another company called American Circuits, do all my high-speed signals with. And they work with you hand in hand to select the material that you're using, specific types, because there's some other special material other than FR4 that are great for high-speed designs. It's a little more expensive, but if you're doing a 4 gigahertz or 6 gigahertz circuit board, what's called SERDES, doing a high-speed signal serial data transmission, it's okay to spend more money on the FR4 or the material. Using FR408, for instance, a high-speed resin is better, and it's stable, and it's impedance controlled. So it's okay. It's going to be an expensive board anyway. So make sure that you pay attention to the physics. Don't use 90-degree turns. Notice what I've done here. I did not do a 90-degree flat turn here. If I see that in your design, I'm going to flag it for you. The reason you don't do that is because a 90-degree turn creates it kind of creates a spot where acid. Remember, these circuit boards are produced using acid, an acid bath. So there's a mechanical process of the PCB being made. And so the thing is, you want to make sure that there is no acid pool that builds up in the corner of a trace. So when it's like a 45 here, it's fine because it'll just sort of naturally roll off a little bit. But if it's a sharp edge, what ends up happening, the acid will pool up and will bite into that corner. And so if this is already 5 thousandths of an inch, as is this trace here, this is 5 thousandths of an inch trace. Now that might bite in 1 or 2, 3 thousandths of an inch. And even though it's only a very short distance, it's going to affect the resistivity, the resistance of this trace. And so I end up with a possible eventual break if the board flexes over time. This board could break. So it'll work fine probably if you use 90-degree turns in the prototype, which for senior design is fine. In reality, it'd probably be perfectly fine. But in practice, avoid doing that, because long term, if you're ever going to do this for production, if you're building 10,000 of a circuit board, you're going to start running into manufacturing issues where this circuit board will eventually have a reject rate. And it's all going to be because of 90-degree turns. So you just avoid that. Instead, just use 45-degree turns. So just do not do this. It's okay to have extra parts on your board, especially debug parts, because remember, once the shape of the printed circuit board is set, once you define the mechanical dimensions, all copper is free. You're paying for that square inches of copper and the number of layers. That's what you're paying for. Once you've done that, how many parts are physically in that area is up to you. You can fill the entire board with parts and traces, or you could be just blank board. It could be completely etched clean. Doesn't matter. That's what you're paying for. They don't charge you for the traces. They charge you for the size. So always plan to use extra parts, have extra connectors, extra I/O. If certain signals are hard to get to with an oscilloscope probe, this is always a very good tip. Always have a separate connector that you can actually hook up a digital logic analyzer or an oscilloscope probe. You can actually buy test points that you solder to the board and actually can clip your oscilloscope to. Highly recommend that, especially you got the space for it, being that this is a senior design project. Please use that. If you're defining the layout of the connector, that means that you can change it to suit your layout. In other words, don't just go port, pin 1 is this, pin 2 is this, and just force it to kind of, you take a look at your layout, and it just would make more sense if, pin 1, if the connector was just flipped upside down or the pins were just reorganized for whatever reason. If pins 5 and 7 were swapped, I could route straight from the microcontroller right into the connector. Well, if you're defining the connector, guess what you can do? You can redefine the connector. I do this commonly. This is a great layout trick. This is one of the advantages of being both the schematic designer and / electrical engineer for the board, as well as the PCB layout artist. Because usually you use a separate PCB layout artist, and it's usually not the electrical engineer. But this is one of the advantages, because usually the PCB layout artist who's doing the work of the CAD design usually doesn't bother to come back to the engineer and say, hey, can you swap pins 5 and 7? That would be really helpful. They just deal with it. And so you end up with these kind of squirrely looking traces. I just go and I go, you know what? I don't feel like routing this. There's better things to be doing in my life. And it really doesn't matter that pin 5 and pin 7 are RX and TX on a connector. Now I'm making it TX and RX instead of RX and TX. Who cares? It makes no difference. It's a harness. I'm going to have a wire hooked up to it. Does it matter that pin 1 or pin 5 or pin 7 is whatever? No. Okay. Now sometimes you don't have a choice. You're the other end of the equipment is very specialized and specific. In that case, you got to deal with it. Deal with that a lot. It happens. But if you're defining it, hey, suit the layout. Make your life easy. Same thing true with microcontrollers and FPGAs. If you're just turning on and off I/O lines and it's not like a bus that is, D0 through D7, like a specific bit order, if it's like solenoid number 1 versus solenoid number 2, and if it just makes flip them around, do it. Because at the firmware level, and this is another thing, I write a lot of my own firmware, pin port 2.1a or 2.1 versus 2.2 is just a defined statement in my microcontroller. If I flip it around where layout was just easier, if solenoid 4 was bit 1 and solenoid 0 was bit 5, well, guess what I'm going to do? Because I'm going to define it in my header file, and from there, the code is going to be written exactly the same. I might just have to flip the header file and how I define my pins. So, and you can do the same thing with FPGAs. It just completely depends on what exactly you're doing. But if it's just I/O controls like motor control or solenoid valves, all sorts of other different functions, as long as the I/O pin is electrically the same, meaning that it turns on and off in the same fashion, it doesn't matter which bit it is. So just remap. Don't just pour a ground plane polygon on the top or bottom layers just because everyone else is doing it, because it's, quote, air quotes here, reduces noise. This is very common. This is kind of, there's truth in this, but, and as everything, there's truth and there's also a bunch of just misconception. You just can't pour a ground plane over a circuit that's especially a 2-layer board and expect it just to reduce noise. There is a bit of Faraday cage stuff going on here, but that really is true when you have uninterrupted copper. If you think about it, I mean, because remember, physics matters. If you have a copper pour on the top layer and you've got a whole bunch of what we call islands and a bunch of broken circuits, well, that doesn't do you any good. You're actually making things worse, actually. You're creating antennas, and especially if it's dead copper, you're going to have eddy currents. It just becomes torturous, actually. It makes everything 10 times worse. So don't just do it because everyone else has done it. If it does serve a purpose, then do it. I do copper pours on sometimes on the back and top side of a board, but usually there are boards where there's not a lot of components and especially not a lot of traces on the top side. Usually I do, we're talking like 20 layer boards, 20 layer board. So there's 20 individual copper layers, a lot of high speed signals going on. Basically, the top and bottom layers are nothing but components and then vias. There is very few traces on the board on the top and bottom side, just components and pads, and everything's happening inside the board. In that case, I actually do pour top and bottom planes because that actually becomes a shield layer. Think about how you're going to assemble the board while designing. Always pay attention to this. Remember, especially in this class, you're likely to be designing this board or assembling this board. So as you're designing it, be thinking about how you're planning to assemble it. If you choose extremely small parts because, oh, that's just great in layout, which is the common thing I do like to do myself, it's wonderful. Do you have a pick and place machine? No. Then you might want to use larger parts. So just be thinking about that. Can you use through-hole parts? Yeah, they're kind of old school, but guess what? Through-hole parts are the easiest things to assemble ever. So be thinking about that. Consider track lengths, and this is kind of thinking ahead to if you're doing designs where you're more outside of this class. Notice this is yellow. This is an actually inner layer board. Consider track lengths. If you're doing high frequency, you're going to have to make sure that depending on what kind of bus it is, you're likely going to have to match trace lengths. In this design here, this was a 6 gigahertz design. This had a big ball grid array chip over it, this FPGA. And notice these little squiggles here where they go back and forth, and kind of have different lengths. And notice this one is, what it says, 1, 2, 3, 4. It's like 4 or 5 back and forth squiggles. And this one's about 6, 7. And this one's but a partial. Notice how each one's different. What it is that this pair of signals is the same length from the end to end. This is the same length as all of these. These all have the same total copper inches in length from one set of vias to the other end. Now it depends that and they did this when they designed the FPGA. They made sure that everything is measured from when the pad hits the boards to where the pad exits the board or the signal exits the board. And I have to keep that length within 10,000ths of an inch, which is about the size of a human hair. And that's because I'm moving at 6 gigahertz. And if you do some computations on speed of light or the speed of the signal, yeah, if 10,000ths of an inch is within the tolerance of where a bit could be toggled. So you want to make sure that you're within that realm. PCB place and routing here. So what we have here is, you notice how I've got everything laid out. Make sure it is, layout is kind of an art form, and I take care in my design. I noticed everything is laid out real neat. This is a production device I have. This is, I've made thousands of these. So notice how everything is laid out nice and smooth. Out of this is an ADD converter. Everything's coming out, going into these resistor banks and capacitor banks, as there's actually a capacitor on the other side. Everything has a via. It's all spaced evenly. It's an art form. I'm not expecting that you will do this level or hopefully would surpass me. I'm not expecting you to have some elaborate design and be manufactured ready, like be able to build 1,000 of these kind of a thing. But take care about how you do it. Don't make sure everything's consistent. Take your time. Care about what you're doing when you're doing these designs. So another thing is a lot of editors, the higher end ones, allow you to do 3D view. Again, this is Altium. So this here is actually this was the project we were just looking at. This one here earlier, the one with the A to D converter and the little resistors. Well, there's that very same circuit noticed right here. That's what the entire design looks like when it's finished. I've even got it where I have the enclosure from PackTech, which is an enclosure company you can purchase. It has all the connectors. I have all of the components have a 3D appropriate part hooked up to it. So guess what the actual final product looks like? It looks exactly like this. It's a great way to get visualization on what you're building, and you can find out if something is interfering, like a connector or something isn't in the right spot. You can visually see that. It's real helpful. In Altium, it's real easy to switch between views. You hit 2 for 2D and basically CAD layout mode, and you hit 3 on your keyboard, and it'll put you in this mode. And you can scroll around and examine your board. Here's another board I have. This is that 20-layer board we were looking at earlier with the long traces that had to be matched. Here's the FPGA we were talking about, mezzanine connector for it to connect to another board, and a bunch of analog, high-speed analog that are coming in. This is for cell phone 5G LTE testing, and with two front-end A to D converters that were converting all of these signals. So this board here was a great example of what I was talking about a moment ago. That this actually has a power and or ground layers on both the top and bottom side that were poured. Because for the most part, other than components, there are very few traces that are on the top and bottom side board. Again, this is a 20-layer board, and we heavily use 3D to make sure that all these components work mechanically in their right spot. And so my client who received this board would take my generated step file for the 3D of the entire assembly and would bring it into theirs to make sure that it would meet up with the mezzanine connector and everything would made up correctly. So because of that, we're talking about multi-layer printed circuit boards. You actually can define, in the case of Altium, but it's true for all software, you can define how you do your layers. This right here is a 6-layer board. In this class, typically we do up to 4 layers for advanced PCB. We cannot do multi-layer in-house at the EDC. We can only do 2 layers. Advanced Printed Circuit Board offers 2 student specials for doing up to 4 layers. That can be any, whether or not you do all 4 signal, do 2 layers signal, top and bottom, with 2 layers internally for power and ground, which is real common, really useful. And also, there's a company out of China, several others, PCBWay.com, for instance, offers really good deals. You just got to wait a little bit longer. I think the turn time is about a week. So you might get your boards in about a week and a half, 10 days to 2 weeks, depending on shipping time. In that, you can actually do 6 layers. I think you might be able to do more than that, but I know you can do 6 layers relatively cheap. And I have approved PCBWay.com. So this one here is an 8-layer stack. And see, the nice thing with Altium, you can also view your stack up and see what it looks like mechanically. This here is the 20-layer board, and this one has a thing called blind and buried vias. And that means if you notice here, we have a via a via is the way you go between all the different layers of taking a signal and coming through and going to either the inner signals or inner planes or to the top and bottom side of the board. Blind and buried means they are just interlayer. You can actually have vias that are only in here. In this case, this goes from the top to ground, top or bottom to ground, and then bottom to layer 7. You can actually define this. This is really complicated and very expensive to do. Only you would do this for very specialized projects. This is something you definitely would not be doing in this class, but I wanted to make sure that you're aware of this. This is a very common technique. Your circuit board that's like in your laptop and in your smartphone probably has blind and buried vias. You'll need to perform a DRC check on your board. If you fail the DRC, design rule check, you must fix the errors. Again, the PCB manufacturer will not build it if it fails the DRC. So again, if you fail the DRC, especially the ones that are built into Altium, guess what? You need to fix it. Again, they will rule check in their own system, and arguing them, as I mentioned earlier, I kind of hammered that home then, It's just a waste of time. Just fix the issue and move on. Once you've got that, now you need to produce your CAM file. So you've gone through this entire effort. Now we're getting towards really the end of it. You've got your design files. You've got a layout. Now you're going to produce what's called the CAM files. Every uh, software is a little bit different. Altium uses a couple different systems. You can do directly right out of your PCB. You can do fabricate CAM files. I use the thing known as an output job file, which is nice because I can put all the CAM and documentation, all these different components of outputting a design. I can put into a job, a script basically, click one or two buttons depending on what I'm trying to do, and it will generate all the files for me. But the minimum CAM files that you need are Gerber files. And Gerber files are an ASCII vector file format. Been around since the 70s. It's what's called a photo plot file. It deals it's truly about photography here, and it's creating these photo plots of all the different layers. If you have top and bottom layer, you got a photo plot for the top layer, you got a photo plot for the bottom layer. If you got power planes in the middle, like a 4-layer board, you have additional couple planes. Every layer has a photo plot. And then you have NC drill file, numerically controlled drill files. Again, these are all going to be machine built in some form or fashion. So the NC drill files defined where a drill bit head goes into a panel that your circuit board is going to be on. So you're going to have a flat of copper, and it's probably going to be, if you're doing a 4-layer board, you're going to have 4 layers that are all glued together, and it's going to drill the holes for your design. So that comes out of the NC drill file, and it tells the computer and tells the drill which drill size to use, basically which hole to use. And usually, if you're using an appropriate shop, the drill size is what that you specify in the CAM editor or in your design is the final drill size. In other words, the final hole size. And when you give that to your PCB manufacturing company, like Advanced PCB, they actually over drill. That means they're going to drill a hole that's a little bit bigger because they're going to plate those holes because it's got to be a via. It's got to carry conductor current through. So for that to occur, they like if you have a 32 thousandths hole, they're probably going to drill 35 and then plate 3 thousandths of an inch. But that is all taken into account by them. Recommended software, professional tools I would recommend is Altium Designer, Cadence OrCAD or Allegro, Mentor Graphics Pads. Those are the ones that I highly recommend. Altium Designer we provide to you in this class. You just need to email me to get on the list because it is a subscription or a license that we have. I highly, highly recommend Altium Designer. Um, a, because I know it really well. B, it's one of the higher end softwares that are out there. And if you learn this is something that you would definitely put on your resume because it's just one of the leading tools that are out there, along with these others. If you have a chance to learn, if you got access to one of these others, I don't. If you say I want to use Mentor Graphics Pads, which I also have on my computer, fine, good for you. You learn pads. In fact, pads is in a lot of ways a higher end version. This is used in a lot of really specialized things. They got some really cool tools Mentor Graphics does. So nothing against pads, love pads. Definitely would recommend learning one because putting any one of these on your resume is a great bonus. Of course, if you learn, there's other ones like Eagle. If you learn and you choose Eagle, make sure you put that on your resume as well. But that's not going to carry as much weight, probably, if you say that you've learned Altium, because if you go to a company, um, say it's a mid-sized business, they make a couple hundred employees, small engineering firm that has 20, 30 engineers, or you might be a more mid-sized, like I said, probably couple hundred engineers, depending on what you're doing. They're probably using one of these tools. And so you want to basically, by you coming in saying, "Hey, I've already got experience with this tool set," that goes a long way in your in kind of an interview process. Because if you come in with like no experience, or if you've been using like a freeware like KiCad or something, well, I'm glad that you know, I'm thinking as an engineering manager, which I used to be, I'm glad you got experience with CAD, but I'm still going to have to expend probably somewhere in the neighborhood between five to $10,000, either in time internally training you or sending you off to get training. So if you're already coming in telling me you know Altium, hey, that means it's going to be more on the job training maybe to get used to our format, but I'm not going to have to train you on specifically how to just operate the software. It's a really useful thing. And there's a lot of free tutorials, YouTube videos, etc. that you have. Definitely learn your tools. So common mistakes, rushing the design. This is really true in this class. You've got other classes, you've got other things you're dealing with. You're in a hurry, you procrastinated. It's now the last 2 weeks of class. I need to get something designed, and you just rush. I've never even loaded Altium before or Eagle. Now you're in a hurry. Well, you're likely to make mistakes when you do that. Don't rush the design. This is a tedious process. It does take time. If you plan accordingly, you'll be fine. If you plan out your schedule ahead of time, you should be fine. Hopefully, you've watched this video early. So definitely do not rush the design. Uh, Not just doing a design review. So you've got a team, and this is to everybody on your team, especially if you yourself are the printed circuit board layout artist of the team. The other team members, you need to listen. You need to do a design review with your design person who's going to be doing the PCB design. Why? Because they designed the board, so they're in very much familiar with it, but they're going to not see the silly mistakes that you might see. They're not going to question, why did we put the connector here? Or wait a minute, my system actually required such and such. You know, those are the things. And don't just be the kind of shake your head, give it 2 seconds of a glance and go, it's okay. Okay, don't be that reviewer. Make sure you take the time. Take an hour, print out the design, go take a Sharpie or take a yellow highlighter and go look at the thing. Ask the hard questions. Go back to the design, specifications. Make sure that things seem correct. Check the silly things like you called out an SO8 footprint, but when I look at the schematic and I look at the bill of materials for the part you're ordering a QFN. Well, this two don't match. So look for the silly mistakes. Another really big thing is trusting online symbols and footprints without verification. I particularly aimed this at our Eagle crowd that uses Eagle because you can get all the snap EDAs. And same thing with Altium. You can also, through Mauser and a few others, you can get Ultra Librarian, Snap EDA. You can get a lot of community-supported footprints and symbols. I have nothing wrong with that. I use them myself. The one big problem I have with it is some of the people who submit, they quote, air quote here, community, some of them are dumb as a box of rocks. I mean, I don't know if they're explicitly just trying to be helpful or if someone used some sort of an auto editor or they're also nefariously just throwing a bunch of parts up there just because and they want people to download it and use it and make a mess. But I have caught quite a few mistakes on Snap EDA, especially on the Eagle libraries. Just verify. Probably statistically, the part you're using is probably fine. But I can't tell you the number of times I've had a student do a design in Eagle, downloaded the part, they get the part, they had the EDC cut the board for them, thankfully, so it didn't really cost anything. They get the board and they go try to assemble it, and the parts won't fit or didn't match. It just was a mess. And then they come, Professor Lusher, what's going on with my design? I downloaded this part, and we go look at the Eagle design files, and I'm like, well, where'd you get this footprint? Because it doesn't look right. Oh, I got it off of Snap EDA. I got it off of this forum post. I said, did you verify it to the datasheet? No. Well, there's your problem. Always verify your footprints. I mean, if you already got a design, great. I mean, let's literally go load up the datasheet, go to the footprint definition, take a couple measurements, verify everything matches. It probably will be fine, but you don't want to be that student who makes the mistake and then now you got to resolder a whole new board. Using an auto router without setting up all the design rules. It goes without saying. Um, again, auto routers are fine if you set up design rules. I hand route boards because I don't feel like spending all that time doing design rules, because I will likely hand route the board faster, and plus internally it gives me assurance that I know what's going on in the board design. Ignoring physics. Again, this is all about traces. If you're doing something that's like, tens of hertz and half an amp or less, you probably can get away with that. So, same thing with trace widths being too small. If it's low current, you're probably fine. If it's high current, yeah, you need to true a trace width calculator. And you verify, physics does matter here as well. Hole sizes being too small. This one's really common. You're going to end up buying components, especially if it's through hole parts, and you don't check the hole sizes. You just went with kind of a default hole size. You get the board that's going to be drilled to a certain size. In this case, you're going to be inserting a round peg in too small of a hole. Well, it doesn't work too well. You don't want to be the ones I've seen where they're trying to wallow out the hole with a small drill bit, or just literally banging the part into the board. Look at the data sheet, verify the hole size. When you do get into assembly, not doing a practice, or actually this is on PCB design, do a test board first. Before even doing your design, go load up one of the tutorial boards, or do simply an LED with a connector and a resistor, something really simple, just to go through the entire process. Don't let your board, your actual board, be the first one you ever do all the way through. Do a real simple board all the way through. You don't actually have to get it made, but just go through the entire process of schematic, symbols, footprints, like literally just a handful of parts, like 4 or 5 parts. Small circuit board, put connectors and pads on it for mechanical placement, define all of the stuff, all of the documentation you may want to include with the design. Go through that entire effort all the way to CAM files. Do that. One of the biggest mistakes is not caring about your job. You're in a hurry, you're trying to get it done, you don't give a crap. This is just another class you're taking. It'll show in your design. Of course, if you have any questions on printed circuit board time, normally I give this lecture in class. Usually I try to have to hurry it, so this is a very long lecture. So if you've got a lot of any questions on PCB design, now's the time to email me or come by my office hours and talk to me about this.